As part of our ongoing study of bullet seating with PounderPress, we've had a unique opportunity to see how this work can be done with the Instron universal testing system. So in this video, please join us as we tell you what we did and the results we got. Here's the outline for our presentation today. We'd like to give you a little bit of background on the project, talk about the Instron 5900 series, and comparing the Instron to the PounderPress, then get right into bullet seating and extraction, provide test summary. Then we'd like to give some insights to the ideas of stress and strain as it relates to cartridge cases. We think of PounderPress as a next generation tool for understanding seating and round performance. It's limited to bullet seating, which is okay, that's what it was designed for. But we only had available time-based force data. We wanted to see if we could evaluate a universal testing system, UTS for short, to see if we can validate the PounderPress methods and data, better understand how the UTS can be used for these sort of applications, and identify a configuration that can be used as a powerful tool going forward for research and development. The folks at Instron stepped up to help. They arranged the demonstration of 5944 UTS, worked with us on configuration and bullet testing and seating and extraction, and then provided the data to us for post-analysis, in addition to a quote we think is quite appropriate for studying these type of applications going forward. We would like to give a big shout out to Joe Lowry, who is the Southeast District Sales Manager for Instron, for doing this demonstration for us. The Instron 5900 series is a very broad family of universal test systems. The ones most appropriate in our work are single column desktop units like shown here. There's tremendous accuracy down to a thousandth of the load cell capacity. They can sample up to 2,500 readings a second, and notice the speed range can go down as slow as 2 mils a minute. It has a customizable control panel here, but it also offers as an option a fully integrated computer system here that runs their Blue Hill software. So there's a very tight integration between the transducer technologies, load cells, and the software, the analytical software that's made available. This is a comparatively small footprint, saves space, and Instron offers literally thousands of optional grips and fixturings for just a myriad of applications. Let's do a comparison between the Instron, UTS, and PounderPress. For bullet seating, the x-axis can be displacement as well as time, but on PounderPress, we're time only. Bullet extraction, again, can be done with displacement. We don't have that available on PounderPress. Feed control is done with a programmable motor. Over here on PounderPress is done with an arbor press, so it's hand operated only. In both cases, we can use the L.E. Wilson dies. Additionally, with the Instron, we don't have to do a separate insert measurement as we have to do with PounderPress. The force range for this particular unit is out to 2 kilonewtons. The PounderPress is 1 kilonewton. So if we score versatility, the UTS offers a tremendous adaptability and functionality. But as we mentioned earlier, PounderPress is basically designed for bullet seating. The software is a fully integrated system called Blue Hill. In the case of PounderPress, we have to run external data acquisition software, and we do our analysis with Excel. They're both desktop form factors. Of course, the Instron is going to be larger than PounderPress, but they still fit on the table. And the availability is you can get the Instron units available off the shelf, whereas PounderPress is kind of more of a proof of concept. These units aren't inexpensive, but considering the functionality and performance and quality built in, I think is very reasonable. We received a quote for the 3343, which is a 1 kilonewton unit. Fewer more modest features, but would be entirely adequate for the work we do with bullet seating and extraction. But of course, PounderPress is a lot more economical. Let's review the seating profile from PounderPress so we can compare it to those from Instron. X-axis is time, y-axis is force in pounds force. When we first start seating the bullet, force increases, but the bullet's not moving into the neck yet. This is called static drift force. At some point, the brass will yield and you'll see a force drop. This occurs at drift Fs max. Now, the bullet-bearing surface is sliding into the neck, and this is called the kinetic drift force. Once the bearing surface reaches the bottom of the neck, you're at drift Fk max, and you'll see another drop in force. This plateau region here is just the bullet bearing surface sliding through the neck. The brass isn't yielding anymore, so this is just the kinetic force of friction, not unlike your high school physics experiment in friction force. Finally, you get to where the drift bottoms out. This distance here from the where the mouth first yields to where the drift bottoms out is what we call the bullet insert depth. That's the total distance being measured going into the bullet going into the neck. On the Instron, bullet seating is very straightforward. I use the compression platings shown here. This is very similar to how we use the contacts on PounderPress. In both cases, we can use the Wilson dies. For those not familiar with this, you see a cross section here. There's a base, a body, and what we call this a seating stem or drift pin. You just pushes down here with the force coming down vertically. This one here just shows a micrometer type top, so you can get precision measurement. But other than that, it's basically identical, except that now we can use displacement instead of time for our seating step. Now here's bullet seating on the Instron. X-axis is compressive displacement because we're pushing down. Vertical axis is force in pound. We have drift Fs max at 30 pounds, drift Fk max at 102 pounds, and then we see a drop down to Fk at around 91 pounds. Notice how the drift bottoms out. They can set the force coming in, so this could be a razor stop point here. You'll also notice how smooth this is. We're going at 10 inches a minute, and we're sampling at 100 samples a second. So we get a very smooth curve off of this. And then now we get to the insert depth at 307 mils. We measured 304 mils on our insert gauge, so it's quite amazing to see that level of precision there. Something also we noticed is now that we're moving by displacement instead of time, this structure is revealed here. We've seen hints of it on PounderPress, but now you can clearly see it develop here. So we don't know if this is the bullet surface accommodating, perhaps burnishing some as it goes in, but certainly very, very detailed information, a very rich opportunity for analysis. For bullet extraction, after experimenting with a couple of gripping techniques, we settled on the advanced screw side action grips shown here. This grips both the bullet and the case. It's actually a massive unit, but it's very gentle. There's also a feature in the 5900 series that zeroes out any compression. So if you look here, you might think as you're tightening this up, it would put force down and additional seating force. It doesn't do that. The system senses this and backs off to keep this at zero force going in. It has, I describe it kind of as a gimbal type technique where these jaws can move around a little bit to give perfect alignment with the axis of force. Down here, the grip grasps the hottest part of the brass on the head, and we notice there's virtually almost no weakness marks for the gripping here. The grip grabs the bullet up here, which of course is a soft jacket and lead alloy material, but even then there's actually minimal weakness marks, and you could probably load and use this over again if you wanted. It's quite amazing to watch this. What comes to mind is a giant robot arm coming down and picking up a pin on the floor. It's quite amazing how they've engineered this. Here's the Instron data for bullet extraction. This is the same sample we just used in the previous seating experiment. Now we're pulling the bullet out, so this is now tensile displacement on the x-axis. The y-axis is still force in pounds. You'll notice the force builds up here till finally the bullet releases. You'll actually see some creeping here, very interesting. We get up to tension, Fs max, at about 107 pounds. Then we're seeing the bullet slide out of the neck, and the maximum there was tension Fk at 95 pounds. And then we continue all the way down and get the extraction depth of 307 mils, which actually aligned perfectly with the seating depth we discovered on the seating part of the test. Now we notice that structures evolve, that we see a structure here when the bullet went in. There was some burnishing maybe on that going in. Now that we're pulling it out, the leading edge of the bearing surface might be burnishing some here. Very interesting. And then we see more structure down here. Perhaps the brass is starting to contract as we pull the boat tail of the bullet out. But certainly, again, rich opportunity for study and very amazing correlation with the seating profile. And here's the summary of our testing on the Instron. To review, sample prep, we're using the 6.5 Creedmoor once fired case. It's not annealed. We're using our baselining techniques for full-length resizing. The interference allowance is set for 3 mils. Wall thickness is 13.5 mils, and the insert depth is 304 mils. We're still leaving the kinetic coefficient of friction at 0.3, and from previous analysis, we know that hoop stress for this sort of a sample should be around 9,000 psi. So for seating, that's a compression action. The drift force static at 30 pounds, drift force kinetic about 102, the kinetic force of friction about 91. This gives a normal force of 302 pounds and hoop stress just a tad under 9,000 psi here. On extraction, we're now the action is now under tension. TFS is up at 107. The TFK at 95, and we calculate a normal force using tension force kinetic instead of the insert force kinetic. We get 317 pounds of force, which gives us a hoop stress of about 9,500, just a scooch above what we expected. So we find it really fascinating that this process is virtually reversible and provides a lot of insight to what's going on with bullet seating. To wrap up, we would like to give some framing and some context to how we're using the universal testing system. Some of our viewers might come to this video from the material testing side versus the folks that will come here from reloading. So I'd like to give some insights. The way UTS is used is in this kind of a stress strain mode. You have samples that look like this. They're going to be composition, type of heat treating, maybe surface treatments, but these are what samples look like. So when they're put in tension, you get a stress strain curve. This one here is very idealized, but it gives you the idea. There's kind of an elastic region, goes into a plastic region, and then the sample breaks apart. Well, when you look at what we're doing with using the UTS for this work, there's a lot more variables that come into play. There's dimensional factors, interference allowance, which is done with sizing, wall thickness with turning, next length with trimming. We also have to deal with metallurgical factors. There's a balance between cold work and annealing that's important. And then there's the tribological factors, polishing and coating, and understanding the surfaces in the neck of the case. But what we see from what we learned here from extracting the bullet, it shows that seating is in this elastic region right here. So once we pull the bullet out, the neck closely returns to its original allowance. This is easy to check with a gauge from ballistic tools, so you can see a measurement of what actually the interference allowance is. So what this suggests is there's residual stringiness in the neck. So we're working in this region here. This also explains that some reloaders don't anneal with every reloading. Sometimes they might not anneal for every 4 or 5 loads, and sometimes they don't anneal at all. They just keep shooting the brass to either the primer pocket fails or you get a fracture, in this case a neck crack. But when the round is fired, we know that the case, the neck in particular, goes up into the plastic region and needs to be returned dimensionally as well as metallurgically. So we think we have a very successful test and a good use of time with the Instron, and we very much again appreciate their help. This completes our presentation, and again we'd like to extend a special thank you to Joe Lowry at Instron for his help with this. As you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. See you soon.